Okay, so now we're going to discuss the right-hand rule, and we're going to do some practice problems involving the cross product. But to even look into the cross product, the right-hand rule states that, all right, if I put my hand in the direction of the x-axis and I close my hand in the direction of the y-axis, this would be x cross y or I cross j, wherever my thumb is sticking up, that's going to be the direction of the vector that is produced by the cross product. So you can see if I did, right, so if I hold my hand in the y direction and I do, okay, j cross y, my z direction is now, the positive direction of the z direction is now pointed downwards. Ooh, that's not good. So let's look at the cross product of this thing. So let's say we did, let's start it up with I cross j. That would be I, j, k, 1, 0, 0, 0, 1, 0. Okay. Well, that would be I. Now remember, if you take the determinant of the first one, when you're looking at I, you're going to take the determinant of this right here, so that would be 0 minus 0. Okay? Remember, it's got to switch to a minus sign on that one, so minus j. So when I'm looking at j, this is going to be 1 times 0 minus 0 times 0, so that's 0 minus 0. And then plus k. Okay, now I'm on k, and so I'm taking the term of the guys right here, so this is 1 times 1 minus 0 times 0, so that's 1 minus 0, so this thing ends up coming out to equaling k. So what is that saying? That's saying I, which is the x direction, crossing with j equals k. Let's see what j cross I is. That's I, that's j, that's k, that's 0, 1, 0, 1, 0, 0. Okay. Now that would be I. Okay, so for I, I'm just looking at these little components right. Oh, no, let's go a little bit. 1 times 0 minus 0 times 0, so that's 0 minus 0. And then minus j. Okay, so for j, I'm looking at 0 times 0 minus 0 times 1, so that's 0 minus 0. And then plus k. Okay, so for k, I'm looking at this component right here, so that's 0 times 0 minus 1 times 1, so that's 0 minus 1. That actually gives me negative k. So that would be pointed in the wrong direction. Okay? So if you did j cross I, okay, so if you're imagining this, and there's nothing necessarily wrong with this, but I mean, all right, so if I'm going to point my hand in this direction and say j cross I, what would I get? I would get 0, 0, negative 1, which it is. It's 0, 0, negative 1. But that's not the vector that you wanted to produce. You wanted to produce the positive z direction. So that's why we do the right-hand rule for crossing these things. So let's do some examples of also finding orthogonal vectors. Okay? Both of those, when you do I cross j or j cross I, you produce vectors that are orthogonal to the ij plane, or xy plane, however you want to describe it. And 0, 0, 1 and 0, 0, negative 1 they're both perpendicular to that plane, but you want to produce the positive one. So whenever you produce a vector that is orthogonal to a plane, well, what would be the other vector that would be orthogonal to that plane? It would be the negative of that vector. Okay? So let's say we wanted to try the problem. Let's say let's say, find two vectors orthogonal to the plane say A, which equals 4, 3, -2, and B, which is going to equal 2, comma, -1, comma, 1. So this would be the statement of the problem. Now, something I might be wondering, why have I switched the language from saying perpendicular to orthogonal? Orthogonal and perpendicular have the same meaning, but mathematicians switched to using the term orthogonal because when you start talking about function spaces, describing one function as being perpendicular to another function doesn't make a whole lot of sense, so we use the terminology orthogonal. Okay, so let's do A cross B. So A cross B is going to equal the determinant. Okay, so we have I, we have J, we have K, 4, 3, -2, and 2, -1, 1. Okay, so that's going to produce one of the orthogonal vectors, A cross B. The other orthogonal vector will be B cross A, which is just the negative of the other one. So all you have to do is multiply all the components by -1. And you'll have the other orthogonal vector. Okay. So I'll do this slowly. Okay, so we're going to start with I. We only got 10 minutes left, so I figured we'll do this one slowly. Although I do have more I can show you. Okay, now when I'm looking at I, I'm covering this up right here. All right. Okay, so this is going to be 3, and then minus -1 times -2. Now, -1 times -2 is just going to become a positive 2. Okay, so that becomes 3 minus 2. Okay, now minus J. Okay, so now I'm covering up this one right here. Okay. So that's going to be 4 times 1 minus 2 times -2. So that's 4 minus -4. And then plus K. Okay. So, all right. Now I'm covering up that one right there. So we're only looking at that guy over there. Okay. So 4 times -1 is going to be a -4, and 3 times 2 is 6. So that's -4 minus 6. Okay. So that's going to equal I, because 3 minus 2 is just 1. 4 minus -4, that's going to turn into 8. So that's minus 8J. Okay. -4 and -6 is a -10, so that's minus 10K. All right, so I think I have done the cross product correctly. How do I verify that I have done the cross product correctly? Now, like I said before, if the cross product equals 0, you have two parallel vectors. Now, if the dot product equals 0, then that means you have perpendicular or orthogonal vectors. So what we're going to do to this this vector, is we're going to do the dot product with the two vectors that we began with and verify that that comes out to 0, because that will tell us that it really is perpendicular to that plane. So, (4, 3, -2), this is going to be dotted with 1, -8, -10. So the first one is going to be 4 times 1. Okay, that's 1. Okay, and then the next term is going to be 3 times -8, so that's going to be -24. And then -2 times -10, that's going to turn that into a positive 20. And yeah, that comes out to 0, so we got a big old check mark for that one. Okay, let's try the other one. 2, -1, 1. Now dotted with that same one that we produced. Okay, so 2 times 1 is 2. -1 times -8 is +8. And then 1 times -10 is -10, so that equals 0. Now we can check mark. Okay? So we could call this V1, and then I would just say that V2 would be -I plus 8J plus 10K. And you can go through and verify that this one is orthogonal to those two vectors, but if you show that the first one is orthogonal to both vectors, well, then if you multiply the thing by -1, it's going to be orthogonal to those vectors too. So those are the two vectors that we can create that are orthogonal to that plane. Are these vectors unique? Not, well, up to scalar multiplication. If you multiply them by a constant, well, think about it. If you're going to do the dot product and you multiply the constant times 0, it's still 0. So they're unique up until constant, which I guess doesn't make them unique at all.